Training a frontier AI model today requires physical infrastructure so massive, we now call them AI factories. These string together tens of thousands of GPUs and consume hundreds of megawatts of electricity. For 60 years, chip designers met growing compute demands by shrinking transistors to pack more of them onto a single piece of silicon. But as we enter the sub-2 nanometer era, that strategy is mathematically failing. AI workloads are multiplying by up to 5 times every single year, outstripping the single-digit performance gains offered by generational silicon shrinks. The root of this problem lies in the physical nature of the electron itself. Electrons possess physical mass and a negative electric charge. When billions of these particles are forced through ultra-fine pathways at gigahertz speeds, they constantly collide with the atomic lattice of the wire and electrostatically repel each other, generating intense friction and electromagnetic interference. Looking at the intricate copper traces on this printed circuit board, we can see the complex physical paths electrons are forced to navigate. This physical resistance causes what engineers call RC delay and Joule heating. In a modern AI accelerator, up to 60% of the energy consumed is wasted just pushing data across these copper lines rather than performing calculations. To manage that wasted heat, facilities rely on heavy chilled water pipes installed beneath data center floors. Pumping more power into these silicon chips will eventually melt them. To sustain the current trajectory of machine learning, the industry must find a way to move data without using the electron. The solution lies in photonics, using particles of light rather than electricity to process and transmit information. Unlike electrons, photons lack electric charge, traveling through glass channels without generating heat. This enables linear superposition, multiple light signals passing through the same space simultaneously. Engineers exploit this with wavelength division multiplexing, merging dozens of colored lasers into one waveguide as independent data channels. This principle is deployed in data centers through co-packaged optics. By placing a silicon photonic engine directly on the same package as the GPU, data is converted into light pulses instantly, bypassing the long, power-hungry copper interconnects on the main circuit board. By leveraging these physical rules, server racks instantly share terabits of information per second across hundreds of meters of optical fiber with negligible energy loss. Light waves can also perform the core mathematical operations that define artificial intelligence. Matrix vector multiplication, the heavy lifting for any large neural network, is a process that normally requires billions of sequential calculations in a digital GPU. Photonic chips compute using Mach-Zehnder interferometers, splitting a light wave down 2 parallel paths. A phase shifter in one path alters the light's speed, delaying its cycle. When recombined, the waves physically interfere. The resulting wave's brightness equals the precise mathematical sum. By cascading hundreds of interferometers into a massive mesh, an entire matrix of weights is encoded directly into the physical layout of the chip. When light enters this mesh, it continuously diffracts, splits, and recombines. The calculation happens passively as the wave flows through the glass. By the time light reaches the photodetectors a few picoseconds later, the complex neural network math finishes, eliminating the need for traditional digital logic gates. Despite the efficiency of optical physics, building a general-purpose computer entirely out of light remains an immense engineering challenge. The modern software world is built on binary code, while photonics operates on analog wave physics. This creates an electro-optic conversion penalty. Every time a photonic chip processes data, that digital information must constantly translate into analog waves using digital-to-analog converters. Once the optical math is done, the signal must be translated back into binary bits. These converters require significant power and physical space. Furthermore, light propagates at roughly 300 million meters per second. Photons cannot be brought to a halt and stored. Without a direct equivalent to electronic RAM, optical chips must repeatedly cycle their outputs back into conventional silicon memory. Because they lack the ability to hold data statically, photonic chips cannot yet perform stateful computing or execute complex logic loops without assistance from electronics. The semiconductor industry's roadmap for 2035 targets a deeply integrated hybrid of electrons and photons, rather than a computer made exclusively of light. On silicon wafers like this one, components are being designed to stack directly on top of each other. In this hybrid layout, electrons are reserved for high-precision logic and memory storage, while the photonic layer acts as the high-speed data highway and matrix engine. Advances in 3D packaging are bringing these layers within micrometers of each other, reducing the conversion penalty. Simultaneously, researchers integrate phase-change materials onto waveguides, creating physical structures that lock neural network weights directly into the glass without using any static electrical power. This transition from electrons to photons resolves the fundamental physical limits of silicon. By shattering the electronic wall, engineers can ensure that the artificial intelligence of the next decade computes at the speed of light.